Welcome you to the final award plenary of the summer 14 meeting. The first thing I have the honor to do is I wish to thank our sponsor, our hosts here at the University of Minnesota. I know that includes more than Ken Heller, but I know a lot of us, when we think about this institution from this organization, that name comes to mind first. How many people thought the Ken Keller building was actually the Ken Heller building when they saw it? All right. This is I arm wrestled Mary for this because Ken has been an amazing mentor to me in getting me going, and in fact talked me into running for my first elected position. Maybe I shouldn't thank him for that. Anyway.
Thank you very much. I want to really accept this in behalf of all the people at the University of Minnesota that contributed so much, and I'm sure you've run across them, and if I go through all the names, we'll be here another 45 minutes, but please thank them. They're often in maroon t-shirts and around making this meeting run. And of course the AAPT staff that has done an amazing job in organizing the meeting, so thank you all.
Hang on. Oh. Thank you. All right, and now it is my great pleasure to introduce Eugenia Etkina. Did I get that? I mean, I've known you for years. Did I get that right? Okay. In receiving the AAPT 2014 Robert A. Millikan Medal, which is for notable and creative contribution to the teaching of physics. She also asked me to be brief because she's got a great presentation, so I don't want to take any of her time. So I'm going to refer you to page 16 in the program for all the details. But there are a few things I just have to say. She started out as a high school physics teacher, and then she made that transition, got her PhD, and now runs one of the most successful high school physics teacher preparation programs in the country and perhaps in the world. And she's also the co-creator of ISLE, right, which is the Investigative Science Learning Environment, and now co-author of a text based on that curriculum. Eugenia?
Hello. Thank you for coming here. And my name is Eugenia Etkina, and the title of my talk is Students of Physics, Listeners, Observers, or Collaborative Participants. And I want first to thank AAPT for welcoming me a long time ago and for being supportive and generous for a long time. And the PR community that became my second family. I tried to find a picture of the APT of 1998 when I first presented my talk, Physics on Rollerblades, but I couldn't, so sorry. This is my student, who is a teacher in New Jersey, Danielle Bouget. With her students, they're not just playing on the floor, they're actually thinking how to design an experiment from which they will figure out the concept of velocity. These are her other students who already figured out how to design an experiment, and they're collecting data to come up with this concept. These are other students, they collected more complicated data, and they're going to invent the concept of acceleration. These are the guys who are doing it. And these are building an experiment from which they will discover the concept of electric power. Those kids already came up with the concept of electric power, and now they're building a puzzle for their friends to solve. They're applying the concept. So why are they learning physics this way? Why are they being collaborative participants instead of just watching, listening, and maybe practicing what Danielle told them, even if they do it in groups? These kids are actually coming up with their own ideas. So it started all a long time ago. As you can hear from my accent, I was not born here. I was born in Moscow, Russia. At that time, it was Soviet Union. And I graduated from the Moscow State Pedagogical University, the Harvard of physics teacher preparation in the whole Soviet Union. And this is the physics department where I went. And then I went to teach in the Moscow School Southwest 1543. The arrow is pointing then around at the buildings. You know, this is where I lived for many years, where I taught physics for 13 years. And although I had a pretty good picture of what kind of physics I'm going to teach, because I was born in a family of physicists, my father was a physicist, I'm like this cousin, my cousin Vinny person, everybody was a mechanic, and in my family, everyone is a physicist. So I had a very good idea of what I want my students to do. However, these ideas changed dramatically after I started teaching, mostly due to the principal of my school, Yuri Zavelsky, who is still a principal after 30 years, and he himself is a geography teacher. So he used to come into my classroom after the lessons were over, look at me and say, are you assessing your students according to Bloom's taxonomy? I was like, didn't say anything. I'll look at him and say, I want to see how you do it. I'll come in 2 weeks and observe. And I will go and find out what Bloom's taxonomy is and how to do it. And in 2 weeks, he would come and observe me. And this is how I learned about group work and Bloom's taxonomy, an individual approach to students, many things that he inspired me to do. And once he comes into my classroom, it was 1984, 2 years after I started teaching. I started in 1982, and he says, what is it that you really want your students to take away from your courses? At that time, and even now, all of students in the Soviet Union were taking physics. There was no exception. How many of my students went on to become physics majors at the university? From 0 to maybe 1%, if 1 out of 30 would go on to become a physics major, I would consider it a success. So of course my students were not going to be all professional physicists. What would they take away from my courses? I started thinking, and I realized, especially talking to my father, a physicist, and observing him work, I saw that the way physicists think was really different from all other people, especially because my mom was a math teacher. I started to bring in these ideas into my classroom. I wanted my students to see that knowledge is built on evidence, that we observe phenomena, that we come with explanations, and then we somehow test them and imply them. And I was showing them how to do it, and they participated in me showing them how to do it. And I was very happy with my teaching until another person came into my life. This is my student, Arkady Ostrovsky, who graduated in 1988. He was a straight A student. He went on to learn how to be a theater director, and now he is a reporter. So he came to have a cup of tea with me a year after he graduated, and we were talking about his university work, and I asked him what he remembers from his physics classes. He got an A, and he said, I don't remember anything but X-rays. I said, why X-rays? He said, remember, I did a presentation on X-rays. I learned X-rays on my own. Well, to say that I was sad after this would be an understatement. I got really depressed for a while, and I realized that me showing them the beauty of physics is not enough. They actually need to participate in the construction of this beauty and see the power of this construction, not just the final product, but also the process. So it's not just the product that is important. The process is the key. And what is the key to this key is, how do you know what you know? If this is the main question, then your whole thinking about teaching and learning changes. Because instead of focusing on what comes at the end, even if it's a 98% on FCI, it's not what it should be. It should be the process of construction of physics. But the same way as physicists cannot do it individually, the students should work together and make physics together. Not read about it in a textbook and then come to class and discuss, but actually see how it is born from experimentation, how it gets tested in experimentation, and how it gets applied. And then they will start thinking like physicists. And this is the thinking like a physicist, what I thought my students should take away from my courses. And so I redesigned the curriculum and implemented it from 1990 to 1995. Students took physics for several years, not every day. It's still more than in the US, but not like 5 years of full physics. It was an amazing success. 10% of my Moscow students went on to become physics majors. And before, as I said, it was about 1 or even less. So they really loved it. And when I came to the US in 1995 to Rutgers, first to the Department of Physics and Astronomy, and then to the Graduate School of Education, I was so excited to share this method with the world. So I wrote a paper to the sent it to the American Journal of Physics about this new method of teaching physics that I created. I got a response in 2 weeks. My paper didn't even go out for reviews. 2 editors wrote a very nice letter saying, Eugenia, your ideas are great. They're so great that we agree with every single one of them, but that's the problem. Everybody knows it and everybody does it because this is what physics is. So we're not going to publish your paper. I was very upset, of course, and at that time, I was working as an evaluator on one of Alan's projects. So I asked him, could you please read the paper and tell me if you know it and if you do it? And so he agreed to read it. And he came back to me the next day and said, you know what, I never thought about it this way. And of course I don't do it, but I've been looking for something like this for years. I want to try this method. And he did. And we got amazing results the first time. After his first semester of implementation. So I rewrote my paper with what students did and explained everything and sent it out to the American Journal of Physics, and guess what? It was rejected. Because they said, you know, that's a great method, but it's so complicated that nobody can do it. So we're not going to publish it. But there were people who believed in it, and this was Suzanne Brahmi at Rutgers and Shuli Zhou at Chico. And we all got together and we wrote a grant to develop this method in detail for American universities and colleges and high schools and many other people over the years. If I put all the pictures here, this would be my whole talk just showing people who contributed to it. Many people contributed to the development of what I'm going to show you later. And we have it now. So I'm going to talk about this system that now is being applied in many high schools and colleges and universities, but at first I want you to experience it, okay? So let's try this approach together. Imagine we do the following experiment. You take a laser pointer and you shine it on a mirror. Raise your hands those who did it at least once in your life. Good. So if you do it, that's what you see. And if you look up closely, you see this pattern. This is looking at the mirror, this is along the ray. So I want you to talk to your neighbor and see if you can come up with a few explanations of what you're observing. Talk to your neighbor for just a minute. Okay. Great. Thank you. I'm sure you have some ideas. We call those ideas crazy ideas. Crazy that you're not emotionally attached to them, they're not your intuition, they're not built on years of your personal experience. These are just crazy ideas that you just built to explain this observation. So these are a few that students came up with. So some of them are based on the wave model, so we have kind of an interference from the glass and the mirror, right? And then the wavefronts come together, giving you constructive and destructive interference, some kind of a Bragg type reflection interference if you have some structure inside. And then there are other models that are students think that there are layers inside, and the reflections from different layers give you dots on the surface. And this would be the first one, would be the specular reflection. But some suggest that there's some kind of a diffuse reflection on the surface, and each point of this reflection is the source of light. And this way, you have multiple sources of light that everybody can see. So these are different explanations that can explain in more or less detail what we observe. And the interference-based models are based on the analogy with thin films when we see light and no light, depending on how thick the film is. So now that we have different explanations, what do we do with them? Well, we need to test them, right? How do we test them? We design experiments and pretend that each explanation is correct and say what will happen as the outcome of the experiments based on the idea that the explanation is correct, even if we probably do not believe in one of them. So let's think of what experiments we can possibly design whose outcome we can predict using different explanations, wave-based reflection explanations, or the explanations that you came up with. I'm sure that you had some other explanations. So one of the experiments would be to take a mirror that doesn't have the layer of glass. All of the explanations that we showed are based on the idea that there's like a film of glass on top of the mirror. So think about what will happen if we do not have the glass, not based on your intuition, but on each explanation. So in this case, if we just take the mirror without the glass, the expensive mirror that we never use, there should be no pattern at all because there is no layer. And that's what happens. You just see one shiny dot. So now, did we prove all of the explanations? Because they all predicted that we will not see the pattern. Well, we didn't prove them. We just failed to disprove them, right? So what do we do next? We need more experiments. And the students suggest, let's take lasers of different colors. If we shine different lasers of different colors on the same mirror simultaneously, then if it is the wave-based explanations, we should see the difference. If it is the reflection-based explanation, we should not see any difference. So we can do it. These are two lasers, and this is the distance between the dots, and we see that the distance between the dots does not change. So the reflection-based explanations, predictions based on them, match the outcomes, and the explanations based on the wave model were rejected. Now, one experiment is not enough. So what else can we design to refute the wave-based model? I want you to think a little bit about it, not too long though. So what else can we do? And the students suggest that we take a thinner mirror. So if we take thinner, when the soap film gets thinner and thinner, then the lines get bigger and bigger, right? Wider and wider. So the wave pattern predicts that the dots should be farther apart, and the reflection pattern predicts that the dots should be closer together. So we have, again, two different predictions based on different models, and this is the outcome of the experiments. The dots get closer together, so we can say waves maybe no, for more, sure, and layers yes. But now we have two explanations, many layers or one layer with diffuse reflections. So what experiments can we design to test one of them? Well, here's an experiment. We take the screen and put it vertically, and we look at the brightness of the dots on this screen. So if you have the layer model, then the only reflection that is really bright should be from the mirror. So the very bottom spot should be the brightest. And if you have this model, then this ray will give you the brightest spot, right? So the second from the top is the first reflection from the mirror. This one reflects off the glass, and this is off the mirror, so this one should be the brightest, right? Here, the bottom should be the brightest. Again, we have two predictions for the same experiment, and this is the outcome of the experiment. The second from the top is the brightest, so we're kind of killing the multiple layers model step by step. So now we can develop this model further and further. It's not just reflections off and off, it's the reflection of the reflection and the reflection of the reflection, and that's how the pattern is wide, not just the line. So we use this ray representation to go deeper and deeper into developing our model and explain more and more features of the phenomenon. So what steps did we take to do it? Observed something. Usually it comes accidentally when we're doing something else, and when we notice it, we'll eventually get a Nobel Prize, and if we don't, then somebody else will, right? We came up with several explanations and used ray diagrams to kind of work through them, maybe at first superficially and then deeper and deeper, but without a ray diagram or a wavefront diagram, we wouldn't be able to even conceptualize what's going on. We ruled them out one by one through new experiments, and we're left with the one that we couldn't rule out. Now we can use it and apply to build something. And in physics, as you know, the application, building bridges and buildings, is the final goal of the exploration that we go through. So this is the process that we just went through, is the logic of the investigative science learning environment. For every concept that students need to learn, we give them something to observe. They come up with the patterns and with possible explanations. Of course, they work in groups to do it because alone, you're limited with what you can do. Then they design experiments whose outcomes they can predict using these explanations. And if the outcome does not match the prediction, then they need to think about revisions, assumptions. What assumptions did they make? Maybe they need more data, maybe they need a new explanation, and then if the prediction matches the outcome, it's a yes. You need more testing experiments until you're really exhausted and say, okay, I give up, cannot rule it out, let's proceed to the application. So this is the logic, the flow, the simplified flow, very simplified. I want you to understand it's not like step by step, but these elements are present and the progression is there. But it's not just the logic, it's also the tool for reasoning. Not having the ray diagram would be impossible to come up with different explanations. Not understanding how to draw wavefronts and how interference works would be impossible. So these multiple representations that physicists use, such as mathematical to describe the phenomenon quantitatively, to make predictions, at every step of the way, these are the tools of physics. They constitute the second aspect of the investigative science learning environment. Learning the tools and repeatedly using them throughout learning of physics is a part of ILE. So how do we know that physicists actually work this way? Remember, if you go back to my principal, he made me think what the students will take from my course. It was the physicist's way of thinking. So do physicists actually think this way? If you will look at the history of physics, we see these elements present. But if we put two physicists in a room and give them a problem, will they actually do it? So we did the study using also an optics experiment, a light cone experiment, published in the American Journal of Physics, actually, in 2013. You take a container with water, put some powder in it so you can see the reflection better, shine laser on top, and have a white piece of paper at the bottom. You see this beautiful cone of light. So that's a pictorial representation of what you see. Why do we have the cone? These are the groups of expert physicists and pharmacists, theoretical physicists, experimental physicists, and pharmacists who were invited in groups of 2 to work on the problem at the University of Ljubljana in Slovenia. And Maja Poklinik, who is the first author on the paper, submitted to the American Journal of Physics, not accepted yet, conducted this experiment when she videoed them, transcribed, and created the timelines of what they were doing. So here you see that when person A is talking, it's red, person B is blue, and working together, purple. These are the things that they do. And this is the time. So it took them 35 minutes to solve the problem. And this is the steps that they took. You see there's a lot of purple here. They work together a lot. And if you look at the progression in detail, you can see the progression from a hypothesis to designing of an experiment to prediction to experiment performing to judgment. They don't know about ILE. They just have this problem and they're working on it. But they're doing it. to see if this is just one instance or it's repeated. Maya Pokliny came up with a new representation of what they're doing. This is a transition graph, and this one is for experimental physicist group. So the size of the circle shows you the relative time that they spent on each step. And the arrows, the thickness of the arrows represents the actual number of times that they did a certain transition. So the thicker the arrow, the more times they did this transition. And the direction, if it's two ways, it means they went back and forth. If it's just one way, then they only went in this direction, from experiment design to prediction, for example, multiple times. And as you can see, we coded what they did with these elements of the Isle cycle. And whatever we could not put, we called other. But the other is very small compared to everything else. It's just the relative percent. And usually, it's when they were thinking what other things are similar or how they can apply it. So if you look for the pharmacists, these are not physicists. They actually didn't even remember the law of reflection. We had to remind them. But they're practicing pharmacists and researchers. So their transition graph resembles the physicists very much. And you can see these arrows that go from prediction to experiment performing to judgment, the thick arrows. And the whole flow kind of resembles the Isle cycle. Then we gave the same problem to the students. These were physics majors in the 4th year of being physics majors. They knew geometrical optics much better than pharmacists. You see that the lines are much thicker because it took them twice as much time to solve the problem, although their physics was fresher. And you see all these random moves that were not present. So they just moved randomly most of the time trying to solve the problem. And this is what they did. This is what experimental physicists did. And you can see this part is much richer than here. In the experimental physics, we see this progression very nicely. And here it is almost non-existent. So what we did, we split their work into two parts. The first 45 minutes, mostly random. And if you look at the second 45 minutes, you see this progression very nicely. So it means that in the second part of problem solving, they kind of became experts. The problem itself, if you just let them work on it, they start thinking this way. And this is a natural way of thinking. We didn't teach them how to think. Actually, these two never worked together and never worked in a group before, because at that university, there's no group work for the students mostly, only in one course that they didn't take. So the summary of the study, it looks like Isle cycle does indeed reflect what experts do. When doing problem solving, the experts collaborate intensely and are not afraid to propose crazy ideas. And novices faced with the same problem at first exhibit different behaviors, but then very quickly adopt. And you think, like, is it like really important that our students learn to think this way? We have tremendous trouble getting them to learn the final outcome, do well on FCI and other tests, and now we're going to add this process to their learning. Well, time kind of demands it. If you're familiar with new advanced placement physics, then these are the practices that students should master and will be assessed on. If you think back about them learning physics through this Isle cycle, you will see that they naturally engage in these practices as a part of their learning. If you looked at the next generation science standards, there's 8 practices, but they are almost identical. So being able to reason from evidence, to work with models, to use representations, to communicate with each other, evaluate what they did, is the new focus of science education. If you look at MCAT 2015, I didn't put it here. These are inquiry skills, not practices. They are identical to those. So why? Why is the focus of science education changing? In fact, if we read next generation science standards carefully, we will find a paragraph that says we always wanted our students to do it, but we just couldn't find a way to do it. But if you don't do it, I want you to read this quote. That's one of my favorite. So if your students do not know how they know what they know, they're not actually doing science, they're doing something else. Like compare Dunkin' Donuts coffee and, Starbucks coffee. They're both coffees, but they're different drinks. So if your students learn from authority and then come and practice in class, that more resembles some other activity, I would say religion, not science. So there's another reason. Life demands it. When I came to New Jersey in 1995, on New Jersey Turnpike, we had 0 lanes for easy pass. There were people, collecting tolls. Now, at some exits, there's nobody, and my exit is just one person. Everything is automatic. There are no more people on conveyors assembling cars. These are robots. So if in 2008, people who lost their jobs were the people who did manual labor. Those who did creative jobs did not lose them. So if you want your students to succeed in the workplace, they need to be creative. They need to think like scientists. And on the other hand, imagine all of our lawmakers would ask the question, how do you know what you know when somebody is giving a testimony in Congress or makes them make a decision? If every citizen in the US could ask this question of a politician, how do you know what you know? Maybe we wouldn't have had the war in Iraq. So do students but we still care about them learning physics as we see it mostly now, with final things, with Newton's second law, with electric field idea, with Coulomb's law, and radioactive decay. Do they learn this if they're engaged in the process? So we did a study a long time ago. This was the first implementation of an IEL course at Ohio State, calculus-based physics, 150 students. The Hake gain on FCI for this course was very respectable, 0.56. It was the first time Alan did it, and I think the students did great. In addition to learning through IEL, through this method, students wrote weekly reports in which they answered the questions, what did I learn this week and how did I learn it? And we looked at the students who came into the course with the lowest pre-test FCI, from 5 to 10 points. There were about 20 of them. Out of those, 6 got really high scores on post-test FCI, and 6 got really low. We called them high gainers and low gainers. We looked at their reports when they said, how did you learn it, and coded what they said with unfavorable codes and favorable codes. Unfavorable, remember, they learned through the process, but they still said, I learned because the TA explained me. I learned because I watched the professor derive it on the board, while in fact it didn't even happen. I learned by reading the book, and I learned by doing an experiment with no reasoning behind. Favorable codes were when the students could actually say how they learned things. For example, observed an experiment, we collected data, graphed it, came up with an explanation, tested it. Or I learned it because I thought about the movie where a similar thing was happening and I could explain it in the movie and in the classroom the same idea. Or I learned it because I compared it to something else that I already knew. So applicability, coherence, and the process were the things that were coded favorably. So now, if we look at what they did, this is just from the paper that we published a long time ago. Look at the high gainers. So they have a lot of favorable codes, and the low gainers have very few. Unfavorable codes, the low gainers have about the same as favorable, but the high gainers don't have unfavorable codes. So they know how they learned something, and the low gainers think that they learned because they listened to somebody. So it is important for the students that they actually know how they learned it. So how do you use IEL approach in the classroom? I'll give you one very, very brief example here. For example, you just finished magnetic fields and you want your students to come up with an idea of electromagnetic induction. So you bring them to the lab and you say, okay, here is a coil of wire, do whatever to make the current in this coil of wire not connected to a battery, and this is a galvanometer that I'm familiar with. If you are in a large room setting, you let them observe the experiment that you perform without saying anything, And then you ask them to note the patterns, record those, whatever they observed. Exciting, right? It is exciting. And somebody who's not a physicist will look at this and like, how boring is it? There's 200 people, 300 people watching this silly movie. Oh my God, it's not just the movement of the magnet, right? You can also move the coil. So students very quickly say that if you move the magnet or the coil with respect to each other, there will be a current. And they can explain it because the movement, there's magnetic force, they know it's fine. So they are successful explaining what they're observing. Okay, now if they explained it, there'll always be somebody who said, wait a minute, maybe it's not the movement, maybe it's the change in magnetic field, but these are usually not heard by the rest of the class. So we asked them to design an experiment to test this idea, and because they already know that a coil with the current in it works like a magnet, they say, okay, let's take a coil and move it. If it is the movement, the relative movement, then the coil in which we have the current, this is the power supply, should produce the movement, the current in the other coil. And they're very successful, and they're confident in their explanation. But those who thought it's the magnetic field, they're sitting very quietly because nobody listens to them. So they observe the experiment, and they're feeling nice about it. And then they see that here, we just had the current when nobody was moving anything. Then the students who had another explanation said, oh, we can explain it. And the group that thought that it was the motion, they're actually glad that their explanation was ruled out, because that's the whole purpose of IEL, that we're learning to rule out, not support. So students are left with an explanation that is the changing magnetic field, and now they can explore it more and apply and quantify and do everything. So if you look at this very, very short example, which is not complete, you can see that the moving magnet and the current through the galvanometer, these are the observations and patterns. These are the two explanations, and for the two coils moving, you can make a prediction. The outcome is yes, so we have the confidence in it. The second, if you accidentally do the second experiment, then you cannot predict its outcome, so you need to revise the explanation. Now, if the first explanation is that it is the changing magnetic field, you can test it. If the first explanation is the movement, you can test it. If they're two together, you can test them. The whole idea is that it's not the right or wrong explanation, it's the testable explanation that is important. So, IEL is a kind of a philosophy for an instructor. It's not a curriculum, it's the way of thinking about learning physics. And for the students, not for the students, and the most important idea of this philosophy is that whatever students do in the classroom, they can explain how they know what they know. And I also want to ask you if you noticed something. I did not ask you for predictions before I showed you the experiment with the magnet and the coil. I did not ask you for predictions before I showed you the light cone. I did not ask you to predict what will happen if you shine the laser on the mirror. Why? For many reasons. And one of them is because I didn't want you to feel uncomfortable when you predicted something that didn't happen. We do not ask for predictions before the observational experiments, because we want the students to see as much as they can and be successful in describing what they see. And then they do not come up with the explanations. They come up with crazy ideas. And all crazy ideas are valid as long as they're experimentally testable. That removes this threat of being stupid in front of others if you take a personal stand behind your prediction, which is usually a guess. And it turns out is that If you strongly identify with something and it doesn't happen, or you receive the negative information about it, it lowers self-esteem. So people usually just don't even pay attention to what doesn't match what they expect. So here we see the three pillars of ISLE: ways of reasoning, tools for reasoning, and practicing applying this reasoning and tools in authentic contexts. I will say a few about it later. So how do you reason, what tools you use, and how you apply it? And the reasoning are inductive and hypothetical deductive, plus a lot of analogical. The tools are different representations, mathematical, pictorial, physics-like representations. Your body is also a representation. And application is developing scientific habits of mind through experimental design. So in ISLE, students do not do cookbook labs. They actually design their own experiments following the same pattern. They are either observational experiments or testing experiments or experiments where they apply their knowledge. So from the instructor perspective, ISLE is a way of thinking about teaching and learning physics. So what will students do to come up with something? This way, the process of constructing new ideas becomes as important as the application. So if it's possible for the students to come up with multiple explanations, great. Sometimes it's not possible. It's okay. It's still ISLE as long as students can test them. Students' ideas play a crucial role. They're not wrong ideas. We're not dispelling them. We never use the word misconceptions. These are the fundamental blocks on which we build their understanding. These are resources. These are facets. This is productive stuff that they bring in when they are developing their crazy ideas. And then they test them and realize that something applies in this context and something does not. Experiments play three distinct roles. They're not demos and labs anymore. They're experiments from which students come up with ideas, observation experiments, experiments from which students use to test their ideas, testing experiments, and experiments where they put several ideas together to produce a practical solution to a problem. Predictions are not personal stakes anymore. They're not guesses and not based on intuition. These are the statements of the outcome of an experiment if this crazy idea is true. If it's true, this is what should happen. If that one is true, this is what should happen. And if it doesn't happen, it's great. It's not bad. Representations are reasoning tools. So mathematics is a tool for reasoning, not something to memorize. In this approach, reading textbook comes after you constructed the ideas, not before. If you want to flip a classroom with ISLE, let students observe things at home through videos, then develop ideas together, and only then read the textbook. So the textbook is not the authority anymore. It becomes a resource, something to review and analyze, not to learn from. From a student perspective, ISLE is when I ask myself all the time, how do I know what I know? This way, it is the skill of noticing and imagination to come up with a crazy idea that is important, not the right answer. Intuition, imagination, everyday experience, these are sources of these ideas that students test. So they are very valuable. These are not the wrong ideas. These are not misconceptions. Search for multiple explanations for the same phenomenon is something very important. So when somebody tells you something, you ask yourself, is this the only explanation or there are more? If we teach people to look for multiple explanations, how much easier our life would be. These explanations need to be tested. Assumptions need to be evaluated. And when we're testing explanations, we're not testing intuition. We're testing the crazy ideas, so this removes the personal threat. So don't be afraid to come up with crazy ideas and make mistakes. And get used to working with others, because working together, it's not just adding minds, it's multiplying and raising them to the powers, unlimited powers actually, right? So do students learn in ISLE-based classroom? Yes, they do. They do. We have very good gains, we have very good scores, but they learn more. The studies show that their ability to use multiple representations during one semester improves dramatically. They actually reason with these representations, like force diagrams and energy bar charts, unprompted when they're solving problems. And that improves their problem solving compared to traditionally taught students tremendously. We also know that they learn how to design experiments, collect and analyze data, evaluate the results, and communicate. We published a lot on this. Many people were involved in this work. But remember, the main idea of IEL is, do students know how they know what they know? So think about your students. If you ask them a question, how do you know Newton's second law? This is what Alan actually did in 2000. This was one of the reasons why he switched to IEL. He just finished the semester of mechanics using his overview case study physics and active learning problem solving sheets. His honors engineers were doing great. He comes to the second semester and asks them, do you remember Newton's second law? And I was in the lecture hall at that time. All hands went up, yes, 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 you know, F equals ma. He said, how do you know it? And the answer was unanimous. He got really upset. But there was a really good reason for him to switch, in addition to everything else. So, let's look at what students who understand Newton's third law, because they gave correct answers on FCI questions on Newton's, all of them answered correctly these questions. What do they say how they know Newton's third law? You have time to read? These are IELTS students. David Brooks students. I want you to look at number 10. And the best part, I have along with others, right? So they work together. So this is David's classroom. These are his students working together, 2 groups at a table. He just gave a talk about how to figure out whether the groups are successful or not working together. This is Rutgers lab. The students just got into the lab. They're reading about what experiment they need to design. They have no guidance for it except what to think about. This is they figure out the experiment, they're doing it, and this is something that they came up with. So they work in groups designing the experiments, and at the beginning we asked them to lift their whiteboards and share. And they said, this is not effective because we're bored sitting and listening. Now they do a symposium. People get up, visit other groups, and the groups discuss with these visitors what they did. This way everybody visits somebody and they share through the whole class. So this collaboration now transcends an individual group. This is the whole class talking together. And I want to emphasize this is what students came up with. They didn't like our lifting whiteboards sharing method. So these are the examples of the labs that students do. And you can see here that you have observation experiments, testing experiments, application experiments. We don't leave them just with one line. We tell them, you know, think about it, draw a picture, what equipment you will use. These are not the questions that tell them what to do, but these are the questions that tell them what to think about. So I'm going to briefly tell you about a study that I gave many talks about, but I think here it fits very well. So we have an IEL classroom where the logic of IEL is transmitted by the person in a large room setting to 200 students. The students work together, come up with ideas in a lecture setting. They have the same problem-solving sessions, and the only difference that they have is the labs. Half of the class has IEL labs and half doesn't. So if you remember the pillars of IEL, all of them have the reasoning and all of them have the tools. And only one group has the practices being developed, the ways of thinking, for 10 weeks. In week number 12, we give them a problem, an experiment to design from the area of physics that they're not familiar with, and then we give them an experiment from biology. I want to focus on just one aspect of what they do. So the control group is doing the same content labs. These labs were written by Alan. They come up with a mathematical procedure themselves. They use representations, but he tells them what to do. The IL lab, students have to design experiments, they're guided by the questions, and they have self-assessment rubrics that you probably heard about. I don't have time to talk about it. So we plant an observer with a group who records what they're doing during the time. Everybody has 3 hours. It's a 3-hour lab to work. I want you to focus on this top layer. The red bars show when the students are engaged in sense-making. The group on top spent 44 minutes doing sense-making, the group at the bottom 17. They left early. Actually, if you run traditional labs, you know students never stay for 3 hours. Is it just a fluctuation? And these were 2 unfortunate groups. This is the data from the semester. You can see that at the beginning, they're kind of close, and then the group that does not design their own experiments, their sense-making goes down, and the group that does IL labs, the sense-making fluctuates but stays about the same. So IL students stay in the room, in the lab room, persevering, doing work much longer than the other group. The total time is about, 1.7 times more than for the regular. They're all paid for the same amount of instruction. They all register for the same credits. They just choose to leave, right? Then we give them a problem. During this transfer lab, nobody has any guidance. Nobody is told what to do or what to think about. Nobody has rubrics. And they don't know the physics. They have to teach themselves physics. Look at that. The pattern continues. The students from the design group, from the IL group, continue to do sense-making, and the students from non-design group, non-IL group, continue not to do sense-making when they have to. And they leave earlier. So this is the total time and the sense-making time for all the groups. We observed 10 groups during this study. The difference is significant. So we see that not only they're designing the experiments, they're actually persevering doing it, and they are sense-making much longer. So if you want to use IL philosophy, we have developed a ton of resources, right? So we have the physics video website that is free for the public. And there's 200 videos arranged in IL cycles, and we're going to actually refilm them with better technology. We have the Scientific Abilities website that gives you IL labs and rubrics and guiding questions. It's all free. We have the offshoot of IL that is called Physics Union Mathematics. Again, we provide the materials to the teachers for free. And finally, last year, our textbook came out. We've been working on it for 13 years. It is totally consistent with IL philosophy and the representation approach. Comes with the active learning guide and the instructor guide. You can use it without using IL, but with IL, it's really great. And I would end my talk here, right? My story is very happy, but it's actually better than that because I have my teachers. I have the Rutgers Physics Teacher Preparation Program. You can see they're doing exactly the same things as you saw Danielle's students doing. And these pictures, I had a ton of pictures. I chose these 2, and then I said, oh my goodness, they're doing exactly the same thing as I showed at the beginning. So since 2002, there's over 70 teachers. The attrition rate is very low. I have about 85% still teaching. IL framework is used in all courses that prepare them to teach physics. These are 5 courses in the program. But IL program graduates take it to the new level. I feel like I'm a coach training Olympic champions. I cannot set any Olympic records. My kids can. So this is one of them, Matt Blackman. You see, he can levitate. And students are really surprised. So Matt took IL to a completely new level. He designs computer games. You probably saw his booth at the exhibit center. This game was played by 2 million people. Tell me about impact, right? It uses multiple representations, and he's designing more that will actually have the whole IL logic embedded in them. But he's not just designing games. It's not like fun, right? This is the data sent to Matt by College Board. He had 50 AP students this year. Out of them, 70% got 5s. This result is consistent year after year. He has been teaching for 3 years, the result is the same. Over the nation's 14%. None of his students got a 1 or a 2. Very few got 3s. The majority is 5s. Year after year. There's another student, Jim Flacker. He's teaching at Governor Livingston. Jim went to NASA a few years ago for an internship. And this year, his students, the students of his school district, 1,500, he organized 1,500 students to submit experiments to be done on the space station. And out of 150 experiments that they submitted, can you imagine 1,500 students designing experiments to be sent on a space station? One was chosen. And these are 6 girls from 7th grade that are going to study how mosquitoes develop in the ideas of what they call microgravity, but we will call free fall. So I just wanted to show you that IEL is a way of thinking. It's not just how to teach physics. It makes people enthusiasts, and they can teach their students to feel the same way. So I basically gave it away. So it's not about teaching people to think like physicists. It's actually about teaching people how to think and to persist. If you know how much you persist predicts your success in future life. So we teach them how to persist. How many of them can we touch? A university professor, about 2,500 to 5,000 students, maybe 10,000 if you teach 1,000 per semester. High school teacher, about 3,000. Just think about these numbers, how many you can teach how to think. A teacher educator. I did a quick calculation. If I continue going like I'm going, I'll reach 250,000. So we can make a change. Thank you very much.
We have some time to answer some questions.
Yes?
On behalf of like educators, homeschoolers, or distance learners, how necessary or is it to have groups for coming up with multiple crazy ideas? In your experience, have you seen individuals being able to go through that important part of the process of finding multiple crazy ideas?
It's a very good question. You can play a role of a partner. You can be this group member who pretends that you don't know what these ideas are and help. But the effect of a group is impossible to overestimate. So I've observed again and again and again giving students something to observe and coming up with an explanation, and one group generating 7 to 10 explanations. And the first 5 are generated by individual members, and then they come together and generate more. So group work is really a very, very important thing. But you can be a member of this group. Yes?
I'm right in front. I'll stand this way. Can you talk a little bit about one of two things, or both? How difficult is it to implement the experimental design-based curriculum in the classroom, or to help teachers learn how to implement that? And if it's not that difficult, why, after 100 years of wanting to implement induction in the classroom, we are not successful at a large scale?
I think that the major obstacle is our way of thinking. I don't know, I don't see Kat here, she's in Princeton. She was given an opportunity to redesign the labs there for, first physics course. And she wanted to implement this design in a section. Professors were sending her emails that you're going to fail. They cannot do that. So first, I think it's our belief that they cannot do it that is stopping us. Second, you have to help them. But you have to help them how to think, not what to do. We're so focused on telling them what to do and assessing them on what they do on the right answer. So when students are coming up with their own experiments, they need to be evaluated on the design, not on the right answer that they obtain. And this is the next thing, that you just have to believe that they can do it, give them the tools, and provide what we call scaffolding. So we provide special questions that are grouped in the sets of questions for observation experiments in one set of questions, for testing experiments another set, and for applications a different set. And then we have a set of rubrics that describes the performance, how well to answer these questions. And then the students can take these rubrics and look at what they wrote and improve them. But very, very important that the teachers first went through this design process themselves, and that they understand that students will come up with a different design, and you need to be smart enough to appreciate it. And so again, what we see during the TA meetings when we train them at the university level, they will probably come up with 1 or 2 designs, and students will come up with 7 different designs. So being able to evaluate it and appreciate it is a task too. But to do any of that, you really need to believe the students can do it. This is the necessary condition. Everything else, I think, is secondary.
Okay, so we have reached the end of our official scheduled time. Eugenia, I think we'll agree to stick around and ask questions for a few more minutes. If you have a committee meeting you have to run off to, we won't frown at you.
Thank you so much. Thank you. Thank you. Okay.
Question?
Come here. Yes.
So this actually connects the 2 questions. Is this on? Hello? Thanks. This actually connects the 2 questions. You said that the students will come up with 7 ideas and the grad students only 1. And if you are working by yourself, somebody can give you some alternate ideas. But if you're working in a group, you will see ideas that you never even imagined. What do you think the effect is of simply realizing that there are ideas that you would never have imagined? What fraction do you suppose that is of the benefit?
You mean in every lab?
No, I mean of the method, just so I get a benefit from seeing an idea that's different, but I get a benefit from recognizing that there are different ideas. What sense is that?
Well, actually, it's quite interesting when they say at the beginning that, you know, I had no idea how to solve this problem, and then I saw these ideas coming up, and now I know we can do any problem together. So it kind of builds confidence and also an ability to appreciate other people's thinking. So it is very, very important. That's why I think that working with other people is crucial, and you can't take it away.
Enjoyed that very much. What's the best way to get to your website so we can find out more about this?
Well, you can send me an email. Is it in the program? Yeah, my email is in the program. Just send me an email. I'll send
Well,
you the link.
I assume that you have a website with some information where you can click on it and find out things that you've written about it. Do you have anything like that?
Yes and no. So
So
just
this-
send me an email, and I will point you to a few of them. There's several, depending on the purpose.
Okay, thank you.
Question. Yes, I can ask it in the microphone.
Yes.
How do you, so it seems like in order to
I
be
just
able
feel
to...
really uncomfortable here.
Okay, so you want to just wander
yeah,
down?
Let me just get
Let's,
down.
we're,